In the strange and unpredictable world of quantum mechanics, the simplest acts of observation take on a weight far beyond anything encountered in classical physics. At the microscopic level, particles such as electrons, photons, and even atoms do not adhere to the deterministic predictability that governs the macroscopic world. Unlike the solid objects of daily experience, which possess defined positions and velocities at any given moment, quantum entities exist in a state of superposition, occupying multiple possibilities simultaneously. A single electron, for instance, does not reside in one place but is described by a wave function, a mathematical entity that encodes the probabilities of all its potential states. This wave function is not just a convenient abstraction. It is the very embodiment of uncertainty, a reflection of the deep indeterminacy that lies at the foundation of reality. The problem arises when we attempt to interact with this quantum system. The act of measurement, seemingly mundane in the classical world, triggers an enigmatic process. As soon as an observation is made, the superposition collapses, and the particle assumes a definite state. The electron is found in one particular location, rather than spread across the myriad possibilities described by its wave function. What is remarkable and deeply unsettling is that the wave function's collapse appears to depend on the very act of observation itself. The implications of this phenomenon are staggering. It challenges the assumption that the universe exists independently of observers, suggesting instead that the mere act of perceiving may be a fundamental aspect of reality's manifestation. This conundrum has perplexed physicists for generations. Niels Bohr, one of the architects of quantum theory, argued that the act of measurement is inseparable from the phenomena being observed. In other words, one cannot speak meaningfully about a quantum system without reference to the means by which it is observed. This principle lies at the core of the Copenhagen interpretation, which remains the most widely taught framework in quantum mechanics. According to this view, the wave function represents a collection of probabilities, and the process of measurement forces the system to choose a single outcome. Yet the Copenhagen interpretation remains deliberately vague about the role of consciousness. Does a human mind need to be involved for collapse to occur? Or is any interaction with a macroscopic measuring device sufficient? The interpretation is silent, leaving a tantalizing ambiguity that has inspired decades of speculation and debate. Experimental evidence highlights the peculiarity of this phenomenon in stark terms. The double-slit experiment, first conducted with light and later repeated with electrons and even large molecules, reveals a universe that behaves differently depending on whether it is observed. When particles pass through two slits without any attempt to measure which path they take, they form an interference pattern on a screen characteristic of waves. Each particle seems to traverse both slits simultaneously, interfering with itself in a way that defies classical intuition. Yet the moment an attempt is made to determine which slit the particle passes through, the interference pattern disappears, replaced by a distribution indicative of classical particles. The mere act of measurement transforms the behavior of the system. The universe, in a sense, seems to know when it is being watched, and the potential outcomes of quantum events become constrained in response to observation. This leads to profound questions. What constitutes an observation in quantum mechanics? Is it the interaction of particles with a detector, or does consciousness itself play a decisive role in collapsing the wave function? Some physicists have proposed that the mind, rather than the instrument, might serve as the ultimate observer. This notion, radical as it seems, arises from the realization that all physical measuring devices are themselves composed of quantum systems. If a device is fundamentally quantum in nature, how can it alone account for the definitive collapse of a wave function? It appears that some additional factor, something beyond purely physical interactions, might be required to produce a concrete outcome. In this light, consciousness emerges as a candidate for the ultimate arbiter of reality. The thought is unsettling not because it is immediately testable, but because it forces a reconsideration of the boundaries between mind and matter. The idea that consciousness could influence quantum events challenges the very notion of an objective universe. In classical physics, reality exists independently of any observer. A planet or a rock does not need a mind to define its position or motion. But quantum mechanics suggests that at the fundamental level, the universe may be more participatory, with conscious observation playing an integral role in shaping the phenomena that emerge from the probabilistic fog of superposition. The implications extend beyond physics into the realm of philosophy. If consciousness is involved in determining the outcome of quantum measurements, the universe is no longer a stage upon which life unfolds. Instead, it becomes a dynamic interplay between observer and observed, mind and matter entwined in a cosmic dance. This challenges long-standing assumptions about the nature of reality and the independence of the physical world. The very act of witnessing could be a creative force, collapsing potentialities into realities in ways that defy simple mechanistic explanation. Experimental investigations continue to probe the boundaries of this idea. Delayed choice experiments, where the decision to observe a particle is made after it has already entered the apparatus, reveal that quantum systems behave as though influenced by events that occur in the future. Quantum eraser experiments further complicate the picture, showing that the information available to an observer, whether known or potentially knowable, can determine the behavior of particles. These experiments suggest that the universe is sensitive not just to physical interactions, but to the presence of knowledge itself, blurring the distinction between objective and subjective realities. Physicists who entertain the possibility of consciousness as a quantum observer face both intrigue and trepidation. On one hand, it offers a potential resolution to the measurement problem, a way to reconcile the peculiarities of quantum behavior with the reality we experience. On the other hand, it opens the door to a profoundly unsettling conclusion, that reality is not fully independent of us, that the act of observation is not a passive witnessing, but an active shaping of existence. The prospect challenges the foundations of scientific objectivity and introduces a degree of unpredictability that is difficult to reconcile with traditional scientific methodology. Yet even if consciousness is not the ultimate observer, the quantum measurement problem continues to expose the limitations of our understanding. Decoherence theory, which explains wave-function collapse as a result of interactions with the environment, offers one resolution without invoking the mind. Nonetheless, decoherence cannot account for the apparent role of information and knowledge in certain experimental outcomes, leaving open the question of whether consciousness has a special status. In the quantum world, the debate remains unresolved, and each new experimental result adds both clarity and further mystery to an already perplexing puzzle. The historical context of this debate is instructive. From Heisenberg's uncertainty principle to Schrödinger's famous thought experiment involving a cat simultaneously alive and dead, the measurement problem has long forced physicists to confront the limits of classical intuition. These paradoxes highlight that at its core, quantum mechanics is not merely a set of equations describing particles, but a framework that challenges our fundamental assumptions about reality. It is a science in which the observer, the act of measurement, and perhaps even consciousness itself cannot be ignored, because they appear to participate in the very unfolding of events. At quantum level, it is in this liminal space, between certainty and ambiguity, that the question arises: could consciousness be the final piece of the puzzle? If so, then the human mind is not simply a spectator of the universe, but a participant in its ongoing creation. The implications ripple outward into philosophy, neuroscience, and even our understanding of free will. If observation can influence outcomes, then decisions and perceptions may play a role in shaping reality itself, suggesting a universe that is participatory rather than purely mechanical. Quantum mechanics, in all its elegance and strangeness, is defined not only by its experimental predictions, but also by the interpretations that attempt to explain its deeper meaning. The mathematics of quantum theory works impeccably. It predicts the behavior of particles, atoms, and molecules with unparalleled accuracy. Yet the question of what the theory actually tells us about reality remains deeply controversial. At the heart of this debate is the role of the observer, the act of measurement, and, intriguingly, consciousness itself. Physicists and philosophers have long wrestled with whether quantum mechanics describes an objective universe independent of observers, or whether the mind participates in the very unfolding of reality. The spectrum of interpretations reflects these tensions, ranging from approaches that minimize the role of consciousness to those that place it at the center of physical reality. One of the earliest and most influential frameworks is the Copenhagen interpretation. Developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, it posits that quantum systems exist in a superposition of states until measured, at which point the wave function collapses into a single outcome. The interpretation emphasizes complementarity. Quantum entities can exhibit both particle-like and wave-like behavior, but the observed property depends on the type of measurement performed. The Copenhagen view, pragmatic in its origins, focuses on predicting experimental outcomes rather than revealing an underlying objective reality. Nevertheless, it leaves open a subtle but profound question: what constitutes a measurement? In practical terms, Bohr and his contemporaries treated measurement as an interaction with a macroscopic apparatus. But the ambiguity remains: if every measuring device is composed of quantum particles itself, how does it produce a definitive result? The interpretation does not explicitly invoke consciousness, yet it leaves space for speculation that an observer's mind could play a critical role in collapsing the wave function. In contrast, the many worlds interpretation proposed by Hugh Everett in 1957 offers a radical departure. Rather than invoking collapse, Everett's framework posits that all possible outcomes of a quantum event actually occur, each in a separate, branching universe. When a particle exists in superposition and a measurement is performed, the universe splits, creating multiple realities in which every possible outcome is realized. From this perspective, consciousness is not required to determine an outcome because every possibility manifests somewhere. The universe is a vast, branching multiverse, and observers simply find themselves in one branch or another. While the many worlds interpretation removes the mystery of collapse and downplays the necessity of consciousness, it introduces an equally perplexing consequence. Reality is infinitely divisible, and every decision, however small, generates countless parallel worlds. The mind, in this view, is merely a traveler through one of these branches, experiencing a single thread of reality. Among interpretations that explicitly consider consciousness, the Wigner interpretation stands out. Proposed by physicist Eugene Wigner, it suggests that the consciousness of the observer plays an essential role in wave-function collapse. In this view, a quantum system remains in superposition until it is perceived by a conscious mind. The act of observation is not merely passive, it is causally potent, shaping the outcome of the quantum event. Wigner's idea is controversial because it challenges the assumption that physics can be entirely objective and observer-independent. By introducing consciousness as a fundamental element in the mechanics of the universe, it suggests that reality and mind are inextricably intertwined. Wigner's interpretation was inspired in part by thought experiments such as Schrödinger's cat, where a system remains in an ambiguous state until observed. If consciousness is necessary to resolve this ambiguity, then the observer is not merely witnessing reality, but actively participating in its formation. The role of consciousness in quantum mechanics also intersects with experiments in quantum biology. Though the field is still in its infancy, researchers have found evidence that living systems may exploit quantum phenomena in ways previously thought impossible. For example, the efficiency of photosynthesis in plants and the magnetic navigation of birds may involve quantum coherence and entanglement. While these processes do not prove that human consciousness directly influences quantum events, they suggest that biological systems can harness and interact with quantum states in subtle, complex ways. This raises the possibility that consciousness, as a product of biological systems, may not be entirely separable from the quantum phenomena that underlie life itself. In other words, the boundary between mind and matter may be more porous than classical physics allows. The philosophical implications of these interpretations are profound. If consciousness is integral to the collapse of the wave function, then the universe is not merely a collection of particles governed by immutable laws. Instead, it becomes a participatory reality, one in which the observer and the observed are entwined. This challenges centuries of thought in which objective reality was assumed to exist independently of human perception. Free will, intentionality, and even moral responsibility acquire new dimensions if our consciousness is a causal agent in the unfolding of quantum events. Decisions and observations may influence not only our subjective experience, but also the physical state of the world at the most fundamental level. Yet, the introduction of consciousness into quantum theory raises deep unease among physicists. Scientific methodology relies on repeatable experiments and observer-independent facts. If the mind itself becomes a variable in experimental outcomes, it threatens the objectivity that forms the backbone of empirical science. Critics argue that consciousness is too ill-defined and variable to serve as a robust explanatory mechanism. Unlike a measuring device, which can be described precisely in physical terms, consciousness resists quantification and remains poorly understood in both neuroscience and philosophy. To claim that it determines quantum events is to step into a domain where the boundaries of science, philosophy, and metaphysics blur. Despite these challenges, thought experiments continue to probe the boundaries of consciousness and quantum mechanics. Delayed choice experiments, in which the decision to observe a particle occurs after it has entered an apparatus, demonstrate that the behavior of particles can depend on future measurement choices. Quantum eraser experiments go further, showing that the availability of information, whether known or knowable, can retroactively influence outcomes. These experiments do not conclusively prove that consciousness is causal, but they hint at a universe in which observation, knowledge, and information are deeply intertwined with physical processes. Such results force a reconsideration of the classical notion of an objective observer, independent reality. Historically, the debate over consciousness in quantum mechanics has been polarizing. Einstein famously resisted the idea that observation could play a fundamental role, insisting that God does not play dice with the universe. He favored a deterministic reality, one that exists independently of observation. Bohr, conversely, embraced the indeterminacy and emphasized the inseparability of measurement and phenomenon. Wigner and other proponents of consciousness as an observer extended this debate into the philosophical realm, suggesting that the mind might not be a mere bystander but a participant in universes unfolding. This tension between deterministic intuition and quantum strangeness continues to animate discussions in physics, philosophy, and cognitive science. Consciousness, within these interpretations, is not a simple or unitary phenomenon. It is a complex, multifaceted entity encompassing perception, awareness, and intentionality. If it influences quantum events, it does so in ways that are subtle, probabilistic, and deeply intertwined with the fabric of reality. Some theorists speculate that the very structure of consciousness, with its capacity for self-reflection and abstract thought, may resonate with the probabilistic, non-deterministic nature of quantum systems. The mind, rather than being a passive observer, may function as a bridge between the potentialities of the quantum world and the concrete experiences of everyday reality. The practical implications of these ideas remain speculative, but they are profound. If consciousness participates in the collapse of the wave function, then the universe is not entirely predictable or deterministic. The observer becomes a creative agent, shaping outcomes in ways that traditional physics cannot fully account for. This could have ramifications for fields as diverse as neuroscience, cognitive science, and even artificial intelligence, where the nature of awareness and decision-making intersects with complex systems. Understanding whether consciousness is a fundamental aspect of reality or an emergent phenomenon of neural processes may ultimately redefine our place in the cosmos. If consciousness is intertwined with quantum processes, the very notion of reality shifts from being a fixed, objective framework to something far more fluid and participatory. In classical physics, the universe is assumed to exist independently of observers. Planets orbit stars in predictable paths, rocks lie where they are, and atoms collide according to immutable laws. The human mind perceives these events but does not influence them. Quantum mechanics, however, challenges this assumption. The indeterminacy inherent in superposition and the apparent role of observation in wave-function collapse suggest that reality may not be fully separable from the consciousness that perceives it. The act of observation, in this view, becomes not merely a passive reception of information, but a potentially creative process that shapes the outcome of events at the smallest scales. The philosophical implications of such a universe are profound. If consciousness can influence quantum phenomena, then the age-old debate between determinism and free will acquires new significance. In a deterministic universe, all events are predetermined by initial conditions, leaving no room for genuine choice. Classical physics, in this sense, implied a mechanistic universe, one in which the human mind merely observes a prewritten script. Quantum mechanics, by contrast, introduces inherent randomness and potentiality into the fabric of reality. The wave function embodies all possible outcomes simultaneously, and only upon observation does a particular possibility become realized. If consciousness participates in this process, then choices and perceptions may actively shape which possibilities materialize, conferring a measure of agency to observers. This perspective reframes free will in a way that challenges traditional conceptions. Free will is no longer simply an illusion overlaid on deterministic processes, nor is it a purely abstract philosophical idea. It becomes a functional element of reality, a mechanism through which consciousness interacts with the probabilistic nature of the universe. Every decision, every act of awareness, may ripple through quantum possibilities, influencing not only personal outcomes, but potentially the manifestation of reality itself. The implications extend to the very structure of causality. Cause and effect, long considered linear and unidirectional, may be more complex than previously thought, incorporating both probability and the influence of conscious observation. The idea that consciousness shapes reality also raises questions about the relationship between subjective experience and objective phenomena. Classical science assumes a separation. The external world exists independently, and our minds reflect it with some degree of accuracy. Quantum mechanics suggests that this boundary may be porous. Delayed choice and quantum eraser experiments indicate that the timing and nature of observation can influence outcomes in ways that challenge classical notions of linear causality. In some cases, the mere availability of information, whether consciously perceived or not, can determine the manifestation of a quantum event. This intertwining of information, observation, and physical reality suggests that consciousness and the universe may be codependent, each influencing and defining the other in subtle and intricate ways. The implications extend beyond theoretical physics into everyday experience. If reality is participatory, then our perceptions, intentions, and choices are not trivial. They are active elements in the ongoing unfolding of existence. This perspective casts human awareness not as a bystander to the world, but as a creative participant. The decisions we make, the focus we bring to situations, and even the act of attention itself may subtly influence outcomes, reflecting a universe that responds, in part, to conscious engagement. This is not a mystical claim, but a logical extrapolation from the principles of quantum mechanics and the observed sensitivity of quantum systems to measurement. The mind, in this sense, emerges as both observer and influencer, bridging the gap between potentiality and reality. From a philosophical standpoint, these ideas challenge entrenched dualities. The Cartesian separation of mind and matter, a foundation of Western thought, becomes increasingly difficult to sustain. If consciousness is implicated in the determination of physical states, then mind cannot be wholly separate from the world it perceives. Likewise, the materialist assumption that reality exists independently of perception is called into question. A participatory universe suggests that subjective experience and physical existence are interwoven, each shaping and informing the other. This has profound implications for ethics, responsibility, and the nature of knowledge. If our awareness helps shape reality, then our choices carry a weight beyond the immediate, extending into the fundamental fabric of existence. This perspective also invites reconsideration of the human role in the cosmos. Humanity has long sought to understand its place in the universe, oscillating between humility and hubris. Classical science emphasized the insignificance of individual observers in the vast, impersonal cosmos. Quantum mechanics, by contrast, intimates that conscious beings may have a participatory role in the universe's unfolding. The act of observation is not neutral. It is entwined with the emergence of reality itself. This notion elevates the observer from a passive recipient of sensory input to an active agent whose presence and awareness may influence the physical world at its most fundamental level. The universe becomes, in a sense, a collaborative creation between mind and matter, where consciousness is both witness and participant. Experimental evidence, while still incomplete, provides tantalizing hints that reality is sensitive to observation in ways not accounted for by classical physics. Quantum entanglement, in which particles separated by vast distances exhibit correlated behavior instantaneously, challenges the notion of local realism and hints at a deep interconnectedness in the fabric of the universe. If conscious observation plays a role in the collapse of entangled states, then the mind may participate in phenomena that transcend space and time, further blurring the distinction between subjectivity and objective reality. While such implications remain speculative, they expand the horizon of inquiry, suggesting that consciousness, rather than being an epiphenomenon of neural activity, may be a fundamental aspect of existence itself. The participatory nature of reality also reshapes the understanding of probability. In classical physics, probability is a reflection of ignorance. Outcomes are determined, but we may lack sufficient information to predict them. In quantum mechanics, probability is intrinsic, representing genuine potentiality rather than incomplete knowledge. If consciousness interacts with these probabilities, then awareness may guide the realization of certain outcomes over others. This introduces a novel framework for thinking about causality, influence, and the interplay between mind and matter. Reality is no longer a passive stage upon which events unfold independently of observers. It is a dynamic system in which conscious participation may have tangible effects. Beyond the theoretical, this perspective invites reflection on the human experience. Our sense of agency, purpose, and creativity may be intertwined with the underlying mechanics of the universe. Decisions, intentions, and focused attention could resonate at a fundamental level, connecting subjective experience to objective phenomena. This is not to claim that every thought instantly reshapes reality in dramatic ways, but rather that consciousness may play a subtle, cumulative role in shaping the emergence of events from quantum potentialities. The mind becomes a lens through which possibilities are filtered, selected, and brought into manifestation. Historically, the notion that observation can influence reality has been met with skepticism and resistance. Science has long prized objectivity, reproducibility, and detachment. Introducing consciousness into the mechanics of the universe challenges these foundational principles, forcing a reconsideration of what it means to observe, measure, and understand. Yet the very strangeness of quantum mechanics, the superpositions, entanglements, and apparent sensitivity to observation, demands that such questions be taken seriously. The act of witnessing may not be neutral. It may be a creative force that shapes the unfolding of reality, bridging the divide between the subjective and the objective, the mental and the material. The notion that consciousness might play a fundamental role in the behavior of quantum systems has captivated minds across physics, philosophy, and cognitive science for nearly a century. It is a concept that excites curiosity, ignites speculation, and simultaneously provokes deep skepticism. The central question is deceptively simple. Can the human mind influence the outcomes of quantum events? Yet the implications of this question are staggering, challenging the core assumptions of modern science. Quantum mechanics, for all its predictive success, leaves open a profound ambiguity regarding the nature of observation and the status of the observer. If consciousness is indeed an active participant in quantum phenomena, the foundations of physics itself require re-examination. Skepticism arises primarily from the empirical rigor that has guided physics since Newton. Science relies on measurement, repeatability, and observer, independent facts. Introducing consciousness into the framework complicates this methodology. Consciousness, unlike a measuring instrument, cannot be isolated, quantified, or precisely defined in physical terms. It is subjective, variable, and complex, arising from neural processes whose full workings remain elusive. To assert that such a phenomenon can collapse a wave function is to venture beyond the domain of traditional scientific validation. Many physicists argue that all observed quantum phenomena can be explained by purely physical interactions without invoking the mind, and thus, consciousness is an unnecessary hypothesis. Decoherence theory, which gained prominence in the latter half of the 20th century, offers one such explanation. According to this framework, the apparent collapse of the wave function results from interactions between the quantum system and its environment. A particle is never truly isolated. It is constantly interacting with photons, air molecules, and other environmental factors. These interactions cause the system to lose its quantum coherence, effectively forcing it into a definite state. Decoherence explains why macroscopic objects appear classical and why wave function collapse seems to occur without requiring a conscious observer. It provides a mathematically rigorous and experimentally supported mechanism that aligns with classical intuition, offering a compelling alternative to consciousness-driven collapse. Yet, even with decoherence, the mystery is not fully resolved. Certain quantum experiments suggest that information and observation, rather than mere physical interaction, influence outcomes. Delayed, choice and quantum eraser experiments demonstrate that the presence or absence of knowledge about a system can retroactively determine the behavior of particles. In these cases, whether an observer knows the path a particle has taken can influence whether it behaves like a wave or a particle. These results do not conclusively prove that consciousness is causal, but they hint at an underlying connection between information, observation, and the manifestation of reality. The very fact that such experiments yield counterintuitive results keeps the debate alive and ensures that the question of consciousness in quantum mechanics remains unresolved. The historical context of this debate is illuminating. From the early days of quantum theory, luminaries such as Heisenberg, Bohr, Schrödinger, and Wigner wrestled with the implications of observation. Heisenberg's uncertainty principle highlighted that at a fundamental level, certain properties of particles' position and momentum, for example, cannot be simultaneously known with arbitrary precision. Schrödinger's cat, a thought experiment where a cat is simultaneously alive and dead until observed, dramatized the paradox of superposition and the role of observation. Wigner took this further, proposing that consciousness itself could collapse the wave function, emphasizing the potential participatory role of the observer. These ideas were, and remain, controversial, not only for their philosophical implications, but for the challenge they pose to empirical rigor. The controversy extends to the interpretation of experimental evidence. Quantum mechanics is notoriously counterintuitive, and the human mind struggles to reconcile classical expectations with quantum behavior. Some physicists caution against anthropomorphizing the universe or attributing agency to consciousness, emphasizing that mathematical formalism alone suffices to predict outcomes. Others argue that the very strangeness of quantum phenomena, particularly the sensitivity to observation, suggests that mind and matter may be more deeply connected than previously imagined. The debate is not merely academic. It touches on the epistemology of science itself, forcing a re-evaluation of what it means to observe, measure, and know. The future of quantum consciousness research lies at the intersection of disciplines. Physicists, neuroscientists, and cognitive scientists are beginning to collaborate, exploring whether conscious processes can influence quantum systems in controlled experimental settings. Studies in quantum cognition, for example, investigate whether human decision-making exhibits patterns analogous to quantum probabilistic behavior. Researchers are also examining whether neural processes may harness quantum phenomena in ways that classical models cannot fully explain. While these investigations remain preliminary, they represent an emerging frontier in which the boundaries between mind and matter, biology and physics, are increasingly blurred. Challenges in this field are manifold. Consciousness remains difficult to define, measure, and manipulate experimentally. Quantum systems are delicate, and even the slightest environmental interaction can obscure subtle effects. Reproducibility, a cornerstone of scientific inquiry, is difficult to achieve when subjective processes are involved. Moreover, the interpretation of results is complicated by the probabilistic nature of quantum mechanics itself. Distinguishing genuine consciousness, driven effects from statistical anomalies or experimental noise requires meticulous design, sophisticated technology, and often innovative methodologies that bridge multiple fields. Despite these obstacles, the potential rewards of understanding consciousness in quantum terms are immense. A deeper grasp of the relationship between mind and matter could revolutionize physics, neuroscience, and philosophy simultaneously. It could reshape our understanding of reality, agency, and the fundamental nature of existence. The prospect that human awareness may be more than an epiphenomenon, that it may play an active role in shaping the universe, is both exhilarating and profoundly unsettling. It demands humility, rigor, and imagination, challenging scientists to expand their conception of what constitutes a causal factor in the physical world. Ethical and philosophical considerations also arise. If consciousness is indeed participatory in quantum processes, then human choices may carry consequences that extend beyond the immediate and observable. The responsibility of observation, the consequences of attention, and the potential for influencing reality are no longer purely abstract ideas. They may reflect a subtle but genuine causal connection. This reframes traditional philosophical debates about free will, agency, and moral responsibility, integrating them with fundamental physics in unprecedented ways. At the same time, it is crucial to avoid overextension or speculative excess. Many claims about consciousness and quantum mechanics verge on the mystical or pseudoscientific. Rigorous inquiry requires careful separation of what is experimentally supported from what remains theoretical or conjectural. The challenge for researchers is to explore these frontiers while maintaining scientific discipline, ensuring that curiosity does not become credulity. Controlled experiments, careful analysis, and interdisciplinary collaboration are essential to advance understanding without succumbing to unfounded speculation.